Good morning, everyone. My name is Steve Popke, and I will be your moderator for the next hour. Welcome to our next session, Utilizing Civil 3D Preliminary Design from Small UAS Data, presented by Mark Schnesk with Seiler Design Solutions. A big thank you to all our sponsors for helping make this virtual workshop happen. We truly appreciate it. Remember to complete the evaluation for this class. A link for the evaluation will be provided at the end of the presentation. An evaluation will need to be completed for each session attended to qualify for your professional development hours. With that said, let's start the next session.
Hello and welcome to the next session from the ACEC Wisconsin 2021 Civil 3D Workshop. My name is Mark Schnesk. I'm Senior Application Engineer with Seiler Design Solutions, Seiler GeoDrones. And in this session, we'll be utilizing Civil 3D in preliminary design using a small unmanned aerial system data. Now, the purpose of this session is to differentiate between the different types of small unmanned aerial systems and the sensors available for them. These include rotary versus fixed wing, the photogrammetry sensor, or a Lidar sensor. When to choose the appropriate type of sensor and model, the benefits of each, vegetation considerations, accuracy versus speed. And we'll demonstrate using some collected data, Lidar data in particular, in a preliminary site design in Civil 3D. Now, what is an sUAS? A small unmanned aerial systems, what we commonly refer to in here as drones. So drones are small, either quad or fixed wing aircraft used to carry a payload in the air for a variety of purposes. They're safe, accurate, and affordable. Most importantly, data collected from small unmanned aerial systems are much more affordable than traditional photogrammetry methods. They're typically used in survey construction, agriculture, conservation, mining, inspection, search and rescue, and more. I have many personal drones. I think they're fun. I like to fly them just for a hobby or for aerial photography. Most systems are automated and easy to operate, though you can manually fly them around and collect data as you need to. So most of the data are on a quadcopter or on a gimbal that can be rotated. They're stabilized, and you can fly and get data in a variety of methods. Use it as an additional tool in conjunction with traditional survey collection systems. Like anything else, it's another tool in the box. It's not meant to replace surveyors or traditional survey equipment, but to augment it. There are a variety of types of small unmanned aerial systems to suit your needs. There are multi-rotor and fixed wing are the two common types. Multi-rotor, also known as quadcopters, or there are other multi-rotor copters with more than 4 rotors. They're small and maneuverable. They're versatile. They're easy to get up in the air very quickly. They have multiple payloads available. Some drones only have a single payload. Some have multiple ones you could put on, including a Lidar photogrammetry module or an even inspection camera. They can be used for visual inspections or search and rescue with thermal cameras. Unfortunately, they have a shorter battery life than fixed wing. It takes a lot of energy to keep that weight in the air. Most systems are going to be able to fly around 35 to 40 minutes on modern systems. Fixed wing aircraft, on the other hand, are used for high-speed, large sites, and they're very efficient. Once they take off, they use the forward speed of the drone to use lift off the wings to keep it aloft. The payload sensors are typically in a nadir straight down only, so there's not a gimbal. They can require a larger open takeoff and landing area. So there's some that require a catapult launch, there's some that take off a traditional method, and there's some that are vertical takeoff with a tilt rotor or tilt wing system to transition from that vertical to horizontal flight. But they still require a lot of open space to land. Both systems can carry either photogrammetry or Lidar payload systems. Now, what is photogrammetry? So we're going to talk about the two most common types of sensors carried. Photogrammetry or camera systems, these are used for high density models They're used based on they're a way of measuring distances using photographs. You can create orthomosaic maps. So if you need a overall georeference orthometric photo of your site or orthographic photo of your site as a background, then photogrammetry is what you need. They're very, very easy to use. They have a lower cost than Lidar. So they're usually the first solution people reach for. They're easier to control. You can control the mission speed, the altitude, and the accuracy are very easy to control. But the downsides are they're dependent on a good quality camera. So you can't just pick up any drone with a rolling shutter camera and expect to have spectacular results. So we're going to use something that has a fixed focused camera with a very large sensor to collect a lot of light data. They're dependent on atmospheric considerations as well. Your lighting condition, your weather conditions, try to fly it in fog, you're not going to get much. So haze, smoke, and all those things can be a detriment to your final solution of your model. And it takes a lot of processing power. So once you collect, anywhere from hundreds to maybe even thousands of photos in a mosaic pattern, you can wait a very long time for the processing. So you can make many hours for your results, and most importantly, the data is not able to penetrate vegetation. So when you're getting your final model, you're getting the top of grass, you're getting the top of a field, you're getting data at the top of a tree canopy, but you're not able to get that absolute ground data below that vegetation. Typical model collection is done very traditionally using a linear pattern. So you set up a mission and the drone flies itself back and forth over a site, turns around, does it again. Think of mowing a lawn. Okay, you're typically going to need a high overlap, anywhere from 80% to 80%. That means each image is only capturing 20% more data than the previous photo. This includes the forward motion of the drone and the side overlap. It requires ground control points for absolute accuracy. Plus, you require some checkpoints too. You're going to want to be able to check your model versus ground control or ground points of known elevation. And typically, you have to fly a little more outside of your area of interest. This can also be a detriment if you're in next to a no-fly zone or a critical sensitive area where you're not allowed to take the aircraft. The processing takes a little bit. Photogrammetry requires processing software to create your model. Typically, we're talking about something like Pix4D or Autodesk Recap Photo, plus Drone Deploy. There are many others available to you. Typical file formats are going to be LAS or LAZ. These are common file formats used by point clouds in any software. Plus, with photogrammetry, you can get, again, that GeoTIFF orthometric photo. LAS or LAZ files must be processed through Autodesk Recap prior to using Civil 3D or Infoworks. Lidar, on the other hand, is ideal for complex terrain with a high percentage of vegetation coverage. So this is going to be able to penetrate through those leaves. Think of standing underneath a tree looking up, and everywhere you can see blue sky, those are the holes that Lidar can penetrate through to get to the ground. It's an active laser source. Stands for laser direction and ranging. Actually, laser detection and ranging. So it's collected in a similar flight pattern. You can set up a flight mission where it flies back and forth to collect the data, or you can manually point the laser sensor at an object and collect data manually. Because everything is geo-referenced in a particular drone, everything can be tied together into a single model after. Okay. You could penetrate foliage. It's independent of lighting conditions. You could even fly a LiDAR system mission in the dead of night. You don't need an active light source. Okay. The intensity of returns can be broken down and used for feature extraction. So because this has an active light source, the laser light goes out, it strikes an object of a certain material, and a certain percentage of that light comes back to the sensor. Different materials give back different returns, and you can very easily see those within your model to differentiate between different types of breaks between edge of pavement, gravel, grass, things like that to pull out that linear data. The cons are they're a little bit of higher cost, and it requires extra time to fly. You can have to fly a little bit slower than you would for photogrammetry, and it requires an IMU calibration. The IMU is the inertial measurement unit within the drone that keeps track of its orientation and position in the sky, along with the GNS RTK solution. Most of these drones nowadays that fly LiDAR and photogrammetry have a real-time kinematic GNSS solution to get that 1 to 3 centimeter precisional accuracy of the position of the drone in the sky. So let's talk about accuracies. We're talking about LiDAR and photogrammetry accuracies. LiDAR, I label this slide LiDAR, but the same holds true with photogrammetry. It depends. LiDAR accuracies depend a lot on your hardware budget. We call hardware budget because as little errors propagate in the drone, they'll trickle down through your final product. So the actual precision of the actual LiDAR sensor itself, the positional accuracy of the drone, either the GNSS solution or the IMU solution, do they jibe, do they cross together? Bore sight alignment, how accurately is it modeled the position of the drone versus the position of the sensor, okay? And any kind of angle encoding error that could come out. Do you have control on the ground? Are you tying your model into control post-processing? Those could be factors in your accuracy. In practice, what we've been finding for modern LiDAR systems is about a 3 to 6 centimeters plus or minus in vertical error. The L1 that we'll be demonstrating today, we've been seeing a mean RMS error of about 3 centimeters for 67% of the points in any band that we slice. So we've been getting about an inch and a half of accuracy. Okay. LiDAR processing requires proprietary software based on manufacturer. May also include third-party IMU software such as POSPAC. So with a system like the DJI M300 and the L1 package, everything's tied together, and a lot of that solution is done within the actual payload itself. Something like a micro drone with an Aplanix IMU, you'll have to run the IMU solution through a software like POSPAC and then tie it back into the GNSS solution and make sure that they merge together so you'll get a corrected position based upon. So it's an extra step that has to be taken. You're going to get out an LAS or LAZ file format. You're not going to typically get ortho photos. Matter of fact, some LiDAR systems don't even collect, and you can't get a color point cloud out of it. You'll have to use some kind of third-party point cloud colorization tool using aerial photography. But other drones or other payloads like the L1 will collect photos and colorize your LiDAR on the fly. Again, data gotten from LiDAR has to be processed through Autodesk Recap. Okay, just talking about the different systems. We're going to do a little demonstration. We're going to focus on LiDAR today. I've done photogrammetry sessions in the past, so this is data that's collected with the DJI Matrice M300 using an L1 LiDAR payload. There'll be multiple returns on this collected data. I didn't touch upon that. For each pulse of light that's sent out, you can get what's called different returns. So it'll send out a series of pulses, and the first object that comes back in that direction, it says, okay, this is my first return. It may be top of leaf canopy or some other hard object. And then the next pulse that comes back could be the mid canopy, and the next pulse that come back hopefully is ground, not necessarily, it's whatever the third object that's struck. And so you can use this in reconstruction and analyzing your model to see if you've actually made that penetration down to the ground. I'll show you an example of that. We processed this in DJI Terra. We did this with a 50% overlap, so every point in our model in 3D space has been hit at least 3 times with the LiDAR. And we're going to create an Autodesk Infoworks model and a Civil 3D site model from it. And we'll do a quick preliminary grading using the grading optimization tools as well. So let's go ahead and dive in. Okay, the first portion we're going to look at in our demonstration is the actual data that was collected using the DJI Matrice M300 with the Zenmuse L1 Lidar package. This is a site we flew for one of our demo days, and I'm just going to go through the software. So once the Lidar comes off of the system, it gets processed and reconstructed in a proprietary software. In this case, we're looking at DJI Terra. Now, with this particular package, pretty much everything is ready to go out of the box. The only things I have done to this is I have applied a coordinate system. So I've shifted my LiDAR from typically drone data is collected in WGS 84 with the ellipsoid height. I've used the software to shift my coordinate system. In this case, this was down in Carbondale, Illinois. So I'm shifted to a known coordinate system. The Illinois West State Plain, NAD 83, and a orthometric height of NAVD 88 conversion. So once that's done, the software very easily collects that data. So I'm just going to rotate around. This is typical for what I would think of for LiDAR data. I have a little bit of noise where traffic was. You can see the color patterns, the way the drone actually colorizes the point cloud is with aerial photos. So as light and clouds change depending on the area that I've collected, you might get some differential. We had a kind of a partly cloudy day, and as the shadows fell in different areas got colorized differently. The more important aspect of a drone or LiDAR data, though, is its reflectivity. So I'm going to switch over to a reflectivity mode. And here you could see a more common pattern that I would see. So you can see the different color bands represent different amounts of energy returning. You can see by the side here. So pavement is going to be in that it's very light absorbing, and shadows in tree are very light absorbing in trees. So they're going to come out in those bluers. The reflective pavement marking is going to be very highly reflective. So you can really differentiate between the pavement marking, the shoulder lines, the paint markings. Here's a fence line, grass. Here's a pavilion and different things like that. The height model as well. I can really easily see the terrain layout based upon the height model. And we discussed returns a little bit. I'm going to switch over to the returns. So I chose 3 returns. The first bounce back of LiDAR was the top of canopy, and then the green represents the second return, and then the red the third. So as I rotate my model around underneath, you can see that we've gotten not everywhere, depending on the density, the type of tree, but I actually have some ground data down here. That's typically more than I would normally get using a traditional survey. So as I bounce around, you can see I have some points that I can use underneath the canopy to get an accurate model for that area. If this was photogrammetry, I would only see the tops of trees and I'd have great big holes underneath where I couldn't get that. Here's another spot, very dense pine tree. Not so much on this one because the density, you could see missing points. I have one rare point in the middle here sometimes. Again, maybe enough to connect the dots to create a point cloud. So this is the LiDAR is its data that it's come off. It's been processed in DJI Terra, and by default, it automatically outputs to an LAS file. So I'm going to get that, and I'm going to plug that in through Autodesk Recap, and then I'm just going to trim out an area. So for our hypothetical, we're going to put a little office building that comes off the road right here with a small parking lot. So let's move on to that. Okay, my next step here is to bring that LAS data. We've gone ahead, processed the data from the LiDAR sensor into its proprietary software, exported it out as an LAS file, and now I'm going to bring it into Autodesk Recap. So I'm going to start a brand new project here. I'm going to import that point cloud. I'm going to give it a name here, so I'll just call this LiDAR site. And then I'll give it a folder where I want to put the the data file. So it's going to contain that RCP, that recap point project file, and a folder that's going to contain the converted LAS to RCS scan. These are the types of files that I can bring into Civil 3D directly. In our case, we're going to bring it into Autodesk Infoworks to process first. So I'm going to go ahead and hit proceed. I'm going to select the file to import. There's my point cloud, so I'm going to choose that LAS file and open that. I'm going to typically look at my advanced settings. So this first one's going to be the intensity of points. If this was photogrammetry, I wouldn't want to touch this at all because all photogrammetry is going to be 0% intensity. There's no active light source. But for Lidar, as you saw, we have that variety of intensity. So I can cull and trim if I want to get rid of dead space or maybe lighten up my sight a little bit. I can bring this up to say, hey, get rid of any points that are below 10% intensity. Maybe they're low accuracy as well. And clip that data and make it a little bit smaller if I wanted to. And under the Advanced tab, I can change my coordinate system. So Recap by default always converts things into meters. But it's a direct conversion from whatever coordinate system I had here. So if I had not used Terra to convert from WGS84 lat long to my state plane coordinate system, I could do that here in Recap as well. But I'm going to leave it alone. I'm going to let the current and the target stay the same. This is going to stay in meters, but that's okay because Infoworks and Civil 3D will make that conversion automatically. So you're going to come out in US survey feet. I can also do a physical decimation of the point in Recap. I can say, okay, every 5 meters. Now, the point cloud you're going to get from the Lidar can vary depending on speed and altitude. I've flown slower speeds, like 100 feet off the ground, AGL at 4 miles an hour, and gotten 1,800 points per square meter. This particular, I think, is somewhere around 400 to 800, somewhere in there, depending on the altitude. I think I flew this at 125 feet, maybe about 11 miles an hour. So we're going to say about 700 points per square meter. That's still a lot of points, more than what I should have to deal with. So I could at least decimate them out and say, hey, if points are bigger than 15 millimeters apart, throw them out of there, so I can get rid of some of that extra point, make my point cloud a little bit lighter. Then I'll go ahead and say, once that's done, hit my import file button on the lower right, and that's going to convert that LAS file over to a recap RCP. Okay, I skipped ahead a little bit. Now that it's finished that conversion, it's opened up an Autodesk Recap Pro. So here's that same point cloud we saw in DJI Terra. It is now in Autodesk Recap Pro. I can maneuver around, I can rotate, I can look at the same viewing aspects that I saw in Terra. Here I have additional tools. On the left side, I can change its look here. As I showed you the different values, there's the elevation view. I can change the elevation range by settings here. I can look at the intensity values. It's using a different color palette, but I can really see it here, the differentiation between the different types of material, especially on my pavement line. This is going to come in handy in Civil 3D and Infoworks when I come to extract some linear feature lines. I could change the lighting to see where the shadows are. You can see the swale there. You can see, looks like there's a culvert opening here that crosses the road with a manhole and additional information. Okay, so once I get this here in a recap, most of the times I'm not going to do much in here. What I will do, I'm interested in this area. This is where I want to put a little a park office with a little drive entrance here and a small 4 or 5 lot parking area. So I'm going to limit my model here for the ease of use. So a lot of times on a model, even to cut out things that I don't want, I'll just do something simple as making a window view in Recap and then clipping that data outside. So this is the kind of data that I'm going to look at. I'm probably going to have a little bit more, so I'm going to unclip And I'll include some of the trees and some of the topos so we can give a frame of reference. Clip that data outside. And then once I get the area that I want, this is what I'm interested in. What I'll typically do is go ahead and export this. So I'll hover over the Home tab and Recap, come down here and move to the Export tool. And I'll export this out. Typically, I call it, add the word clip to it. So I maintain the original. The nice thing about Recap when you're exporting or what they call consolidating is a single scan. So if you had multiple LAS files in here, you can combine them into a single. It's what you see is what you get. So I don't have to worry about deleting points. I could just use this quick clip box to limit what I see, and that's what I get when I export out. So I'll go ahead and make a new file of this using that export tool. It's as simple as choosing this tool, giving it a name, pressing the start, and letting it go. Okay, we've gone ahead and processed our data in DJI Terra, run it through Autodesk Recap, and now we've brought in our Lidar point cloud into Autodesk Infoworks. I've created a new project. I've set the project coordinate system to match the project coordinate of my site, and I brought in my clipped Recap point cloud. So the first thing I'm going to do is I've made a couple of new proposals. Typically, I would have a master proposal for my point cloud. And now I'm going to run through the point cloud processing to start creating my existing ground terrain and extract linear features. So under point cloud here, I'm going to hit the point cloud terrain button. And then for this purpose, I'm just going to leave the defaults here. I've gone over this before in previous classes. We're going to set the optimum ground output. That'll be a 1 meter by 1 meter normalized point cloud. We'll densify point clouds where it detects linear features automatically, so it'll throw more points back in those areas. I'm also going to extract some vertical features and convert those to Infoworks 3D objects that will export out as Kogo points into Civil 3D. And then I'm just going to go ahead and hit start processing, and it's going to start creating the point cloud terrain at this time. Okay, my terrain surface is now complete. It just took a few minutes. You can see I have some overlays and terrain in my Model Explorer. I can show you the terrain looks like. I'll go to the Model Explorer and turn off the point clouds so you can actually see the surface. Okay, and it's made a nice little overlay based upon the point cloud data. So now I'm going to use the point cloud data in conjunction with the terrain to extract linear features. I'm going to go ahead and extract the pavement and shoulder lines and pull out some objects here. Maybe I did additional brake lines where I think I need them for the ditch lines and stuff. So I can bring this into Civil 3D and make a nice Civil 3D surface out of that. So to do that, we're going to go ahead and set a point cloud theme. Now, to help me along with extraction of point cloud objects, I would typically go ahead and set a point cloud theme for showing intensity. Now I've made this up. I'll show you how I made this really quick. I've added a new point cloud theme using the green plus. I'll change the type to intensity. By default, the intensity is a black and white. I usually set this to red to blue and change the palette type to HSV counterclockwise. That'll give me a nice rainbow color, similar to what I saw in Recap. I'll also increase the number of rules to like 25 to give me some more values, and that will give me a nice point cloud intensity themed visualization that I can use when I'm extracting the linear features. Okay, I'll then make a view style called extracted view, and what this view style does in Infoworks is I turn the terrain opacity way down. I also get rid of the sky and brightness and basically any of the rendered items. So all I'm dealing with basically are the point cloud and the terrain. You can barely see it. If I turn it up, you'll see it below there. I'll turn that down because the linear feature extraction requires both points and the terrain, this gives me the best of both worlds. I'll leave the contours turned on as a frame of reference, especially when it comes time to extract things like ditch lines or something like that if I feel I need to extract that additional information. All right, to start my linear feature extraction, I'm going to choose the linear feature extraction tool up here. I'm going to turn off my view settings so you can see better. Under the Manage tab. So once I start this, you'll see I have my dialog box right here. I can move it around the window. First thing I'm going to do is choose a style. So like the first thing I'm going to extract maybe will be these pavement striping. So I'm going to choose a manual style. So when I export this out into Civil 3D, it's going to come out as shapefile data into 3D polylines. And if I bring in the object data will have the attributes of whatever type this is. So if I get lost, I can select the object, look at the object data and say, oh, this is a paint stripe, or oh, this is a break line. So I could choose a variety of different pre-made styles in Infoworks. If I click on the box and choose more styles, you can see the default styles that are in there: bottom of curve, top of curve, paint stripe, passing lane, etc. So I'll choose paint stripe and choose OK. Now I have an automatic or a manual mode. In manual mode, I just pick points in random, and it will, just like drawing a polyline in Civil 3D, it will create a linear feature by points in Infoworks. But there is the automatic mode, and for Lidar, I don't have to choose UAV compatible. I'm going to go ahead and click on this button, and then here it says pick the first point. So I'm going to choose a point here on my stripe, and I'm going to move ahead a little bit, and I'm going to double click further up the road here, maybe a little less, maybe about 20 feet up, 25 feet up, double click, and it's going to find that pattern and follow it all the way down. Now it may get lost, once it gets up there. Once I hit escape on the button, you can see the vertices in there. I may have to slide them and adjust those. If it was a curve feature or something like that, I can right click on this line and say show cross section view, and you would see where that point lies in my cross section. So I could use the vertical tools here to shift it around as I need to, and it creates a new vertex. So if I moved it up here, you would see the vertex it creates. So I'm going to move that back to where it should be, right about there. And then I can use my tools here to move up and down station to make that correction as need be. Specifically valuable for curb lines and things like that. I'll go ahead and do another one. Let's go ahead and do the center line of the road. So vertical feature extraction, I'm going to change my type to center line. Now for pavement striping like this, where it's broken, you start at the beginning of your pattern, go entirely through that first skip and beyond the second point pattern. So it'll detect this skipped line here, this dashed line. Oh, let's try that again. Sometimes I amaze myself. Let's try it again. Click, click. There it is. Now it got it. So now it figured it out and followed that down. And again, I may have to come through either by grabbing vertices or the legs and manually, bring those back. And then it'll adjust the elevations it needs to for those objects. And I'll follow that down. Now I got to pull it back here a little bit, so I'm just going to grab it and bring it back. I'm going to leave that in the video because every once in a while you're going to get those kind of errors, so it's always good to see how you can correct that. And I'll continue on for edge of pavement and, fence line if I wanted to. So I can see there's a break line here. I may choose linear feature extraction, go to manual, choose to a break line style, and just manually, like I said earlier, just pick some points along that break line, and that will help me define that break line back in Civil 3D if I really need it. Skipping here a little bit, I've gone ahead and extracted the remainder of my lines that I am interested in. I'm not going to touch this side as much, more in tune to details on the right side here. I've also gone ahead and done a vertical feature extraction. So under the point cloud tools is vertical feature extraction, and it will run through and identify features that it thinks are vertical features that I can add to my model. By default, it's going to be one of the 4 types here, tree or sign or unknown. But once you place the object, you can go ahead and, if I said, hey, this is supposed to be a pine tree here, I can double click on that and change the manual or the rule style for it and say, oh no, this is supposed to be a pine tree or something like that, and make that update. So that'll go ahead and change those objects if I need to after the fact. But they'll come out of Infoworks as Kogo points when I do my extraction. Okay? So the next thing we're going to do is extract all this data out. So once you've gotten your data together, under your point cloud tools under the Manage tab, you're going to come down here to Export Point Cloud. So in the Export Point Cloud, it's going to export out a brand new RCS file, or a recap scan file. And instead of being these thousands and thousands of points, sometimes millions of points, it's going to be whatever the vertical terrain, when I created that terrain, that density I set. So for optimal, it'll be a 1 meter by 1 meter grid. Kind of if you went out in the field with a rover and shot, just a grid point of topo out there. We're also going to extract out our linear features as an Esri shape file. These will come into Civil 3D as 3D polylines. So once I get my base surface made with the point cloud, I'll add these lines back in to bring in that extra detail back to my model. Under the transverse vertices, for each of these, I could have cut cross sections in the tool called transverse vertices. So to identify that, you could pick one of these lines and say generate transverse lines. It'll go ahead and create cross sections. These come in as a cross section Kogo point, and I haven't really found, to be honest with you, a tool where I would need this. Maybe if I was doing a river section for RFA or something like that. But those will come in that way. And then my vertical features, I chose to bring those in as a CSV. Very important, if you left your original coordinate system in WGS84 lat lon, it's very important that you change your targets to whatever projection you're going to need in Civil 3D, because if I'm dealing with US foot, WGS 84 is in meters, and it's going to bring in all the elevations for these linear features, in meters, and it's going to really mess up your point cloud if you don't do that. So make sure your target coordinate system matches exactly what you want, and then just go ahead and start export. So we'll do that, and then we'll jump over to Civil 3D and create our existing surface. Now we've moved over to Civil 3D 2022. I've gone ahead and exported all my items from Autodesk Infoworks, my linear features, my vertical features. I'm now ready to make my surface, my existing ground surface here in Civil 3D. So to do that, the first thing I'm going to do is import my point cloud. So I've already gone ahead and set up a project coordinate system in here for the Illinois State Plains West, since I'm down in Carbondale. I'm going to say insert, and I'm going to go to my attached point cloud. So now I'm going to come to this export. Now, by default, it's looking for point cloud project RCP. Because Infoworks exports as an RCS file, I'll change my file as a type to RCS. There's my exported point cloud. I'm going to go ahead and open that and just drop it into place. So there's my 1 meter by 1 meter gridded point cloud. From there, just as I would with a normal point cloud in Civil 3D, I will select it, and in my ribbon, I'll choose the Create Surface from Point Cloud. Now, this shouldn't take any time. I'll give it a name. I'll call it L1 Site _ EG, and I'll change the style to Contours 1 and 5 background. I'll say Next. I'm going to do the entire point cloud. There's only 7,600 points in this. It'll go very quickly. And then because this is extracted already as ground, I don't have to worry about filtering. You choose no filter here to make sure you get the entire one. Then go ahead and create surface. As always, it's creating with this routine, it'll create the surface from that extracted point cloud in the background. It really just takes a couple seconds, and there's my surface. So you can see there, it's the location where the culvert was. Here's my land area. This is where that pavilion was in the tree area. So now I'm going to go ahead and add my linear features. So to do that, I'm going to use the map import tool. And then once I start that, I got to make sure I choose the files of type Esri shapefile. So here are all my linear features that I extracted out of Autodesk Infoworks in that folder that I placed them in. I'm going to select that and click OK. And in the dialog box here, I'm also going to choose the Add Data button. And then choose Create Object Data. This will add that, remember that style like paint stripe or break line. It's going to add that indicator as object data to these polylines. And then I always choose import polylines as closed polylines, even though I don't have any. It's just a habit to make sure I don't get any solid shapes. And when I click OK, there's the linear features I extracted. So if I select on this line, I can look at my object data and look, it's a linear paint stripe. And this is a center line, and this is a edge of pavement, and so on. So I can use this to go ahead and change layers and things like that of these lines. So I'm going to go ahead and do that. We'll come back in a different model here very quickly. Okay, I've gone ahead and cleaned up my drawing a little bit, brought those Kogo points in, the trees that I extracted, as well as changed the layers of all my different line types. I've now gone ahead and created an existing site plan too. So this could be a proposed site plan. It's just going to be consists of a building with some sidewalk, a parking area, and an entrance off of the road. So, and I've also delineated an area of my grading limits. So very quickly to show you how quickly we go from Lidar data to creating an existing surface model to creating an AutoCAD background drawing, adding some 2D geometry. By the way, all this geometry is at 0 elevation. So this is just 2D quick sketches. Now we're going to go ahead and switch tack here. We're going to go to the new Autodesk grading, where it is, analyze the grading optimization tool. And when using this, you're going to need a series of lines and closed polylines to define your geometry. So I'm going to go ahead and choose my grading objects. And this opens up a tool palette that shows the different types of grading objects that I can apply to my drawing. This has been covered in other videos. Autodesk has put out a complete series. John Sayer does a wonderful job at going through the preliminary. There's a little 3-step or 4-step video. But just to cover what's going on here, I could take these 2D objects and create a preliminary grading plan based upon my LiDAR. I'm going to go ahead and set a grading limit. And I'm going to choose that outer polyline. And I'm going to say this is going to be max slope 33, min slope 2%. I'll call this grading limit. Okay. You could choose depth of material, whether or not I want to make this a break line. This is going to be a grading limit, and I can change the color. Okay. So I'm also going to set this as a building pad. So I'm going to choose building pad here. And I'm going to set this with a constant elevation of 440. That's about 2 feet or so above my center line of road for drainage purposes. Okay. I'm going to make this area here a sidewalk. So I'm going to come down here to the sidewalk aspect of it. And I want to set this max slope at 2%. Okay. So ADA requirements, this is going to be a 2% slope at max. I'm also going to change the inclination to 90 degrees. Now this inclination says it's going to slope to the north here. That's where my triangles are going to fall, and it's using the AutoCAD angle. So 0 is to the right, 90 is to the north. Okay, I could set my depth of material 0.5 or 0.33 for grading calculation purposes. This is going to be my parking area, so I'm going to set that as parking lot. Okay. Or actually, I'm going to set this as an accessible path. So that will make sure this limits. So I'm going to have at least one handicap spot in there That means max slope 2%. It's going to treat that. And again, I'm also going to make this an aligned surface. That means it's going to align itself with this sidewalk and follow that same pattern. Okay, so no place in here should be more than 2%. Finally, this area is going to be parking lot. It will treat that as a parking lot area and grade it appropriately. And then I'm just going to make this last one here a grading zone. Okay, so this is going to grade down. Now, because this touches my grading limit line, this line here is going to lie on the existing pavement and it's going to match in. I also have a line that I had in here. If I select it in there, and I'm going to set that as an aligned edge. That means the triangles are going to line themselves up along this edge here really nice when I run the grading optimization tool. So once I set all my attributes, and you can go to the help file and find what all the different attributes, grading optimization tool attributes are available. So once that's done, I'm going to start the grading optimization tool. Now, keep in mind, this tool is part only available in Civil 3D 2022 at this time and is only part of the AEC collection. So if you do not have the AEC collection, you will not have this tool available to you. So once I bring it into the optimization tool, here are all my boundary areas. You see there's my sidewalk. I can modify them in here instead of having to go back to the drawing if need be. So I can run different optional tools in here. I can set my settings here. These are some global variables, number of iterations I want to run. Maybe I'll jump that back to like 50,000, keep that a little bit small. It's the number of trial and errors it does. Here I can set some preferences, the mesh quality. The higher the mesh quality, the sharper the edges are going to be. I like to keep it on medium. It's going to automatically refine, remove existing ground points if I need to when I bring my surface in, and I can customize some additional options. Once I do that, I'm going to start the Optimize tool, and you can see it starting to grade my site based upon the rules I tell it. The grading limit will be on the outside. It knows what this pad is. It knows I want to grade the sidewalk out, plus every other limit will get applied to that. So as I'm running this tool, I can look at my convergence. I'm looking for this solution to come down towards. The closer it gets towards the bottom to 0, the better my solution is. I'm looking pretty good here. You can see my cut and fill variables. I can make some changes here, how much weight to put towards cut and fill, how smooth I want my terrain. I can just look at this convergent plot to see how well that's coming out. Once I get a solution that looks pretty good, I go ahead and I can stop this grading and I can send the optimized result back to Civil 3D. I can also bring these items in as feature lines, points, and surface data. Give it a new name. Call this parking preliminary or whatever I want to. And let's change that to a lowercase a and give it a style. We'll give it a style of 1 to 5 design. So it's reading these styles from my civil drawing and say finish. And then there's my surface back in Civil 3D. Then I would typically take, once it's in Civil 3D, it gets treated like any other surface. And I can go ahead and add like a boundary to it of this grading limit line. And then cut that off. So there's my surface. I can look at it. And let's take a look what it looks like back in Infoworks. Okay, finally I've taken my Civil 3D model, saved it, brought it back to Infoworks. So I exported those areas out that I used to create my preliminary grading, the parking area, the sidewalk, the building, and my grading limits as coverage areas. I exported them out as shape files, brought them in as coverage areas back to Infoworks, applied some materials. I've added some flourishes like a person, some light posts, a vehicle, the pavement striping I manually exported out and brought in. So you can see how quickly this was all done, not much longer than the length of this video to process from Lidar to a preliminary design model that I could take in front of a customer and say, this is our design intent. So total time really spent on this model is about 3 hours. That's including the 6 minutes it took me to fly the site with this LiDAR data and maybe the 12 minutes it took to convert that to a LAS. This is the power and benefit of using aerial LiDAR for preliminary grading. It is very, very easy and quick to use. Well, I thank you for your time. I hope this has given you some ideas of things you can do with aerial LiDAR from small unmanned aerial systems. If you have any questions, please don't hesitate to contact us at cadtechnical@silerinst.com. You can also contact me direct at mshinesk@siler-ds.com, as well as Andrew Robb at arob@silerinst.com. Please follow our blog at https://www.siler-ds.com/blog for news, tips, and tricks from Autodesk, as well as any kind of drone data, drone information, GeoSLAM, PointCab, or other programs in the geospatial survey. You name it. We cover a little of everything and are happy to help. Please don't forget to fill out your evaluations at the end. There'll be a link provided. It'll be at the end of the session, and share your thoughts when you're done. Thank you very much. I hope you enjoy the remainder of your session. And I thank you for your time. Bye-bye.